We are now recording. All right, welcome everybody. Today is the 19th of October in Dallas, the 20th of October in New Zealand, and you have joined or are watching in arrears the Robot Builders Night Virtual, hosted by Dallas Personal Robotics Group. I am Carl Ott, the current president for another couple of months and facilitator of our evening soirees every Tuesday night. And what we're going to do is go around the table and share updates from our recent projects and ask questions if we have them. And also, before we get started, one more thing. Just as a reminder, we have this Discord server. There's a lot of activity going on there. If somebody wants to join, let us know, and we can share a link, a fresh invitation. I was looking around. I'm ever watching to the calendar, and I think we have some speaker options for DPRG in December, at least one, maybe two, potentially. But for November, we don't really have a speaker. But on the other hand, that's the bad news. The good news is that Seattle Robotics Society has their second part of the 2021 virtual Robothon. And so one option we have for November is to do it as we did before. Take a cop out for your president and go flash mob Seattle instead of have a regular meeting here.
I have an alternate suggestion. I would like to volunteer Paul to talk to us about his work as a professional roboteer.
Paul has accepted that challenge, but he is one of the two we're talking about for December or maybe after. Still good, Paul?
Yes. I'll be down in the Big Bend. Unfortunately, I've been traveling for all of the monthly meetings, and I'll be in Big Bend during the November monthly meeting. But yes, I've got some pictures lined up and some block diagrams and to talk about how they architected the system. So I think hopefully it'll be interesting.
I have never in my life heard anybody use the sentence, "Unfortunately, I will be in Big Bend."
Okay. Unfortunately, I will not be able to attend the November meeting.
Very nice. We'll be with you in spirit, Paul. But November's far enough away. If somebody would like to present or has an idea, can help arrange a speaker, then jump in there. But otherwise, I'm going to propose we take the easy way out for me. Okay. With that in mind, we have the following people lined up to show what they've got going on. We've got Ray first, then Kumar, then Dave Anderson, then me, Carl. So, Ray, take it away. What you got?
Okay.
Uh-oh. There he is.
Okay, I have a short video of, can you see that?
Yep.
Okay. Anyway, this is a video of one of the mower platforms. And, I had stuck tape on the floor to try to figure out what the path was. And that I could kind of tell what was going on, but decided to stick basically a pretty good size, felt tip marker on the back of it with a clip, I think the largest paper clip you can buy. And my wife was gone, so her, where she parks her car in the garage was available. So I made use of it and traced this out. And let's see if I can get it to play. Okay, where the heck is the play button? Oh, come on. There it is. Okay, what I did. Can you hear that? Put a pin.
It's very soft.
Okay. And it generated this pattern. So going up. Okay, what about now? Around one wheel.
Better.
180. Okay. Coming back, pivoting on the other wheel. That's this.
A little bit more
here. Coming back, several times. I tried to do the Doug method of sticking tape on stuff, but that didn't work too well. Anyway, the pin was back over, stuck on this wheel, just with a clip, so it's not held super precisely. It's, can wiggle around just a little bit. It's not a perfect fit. Anyway, the distance between them seems pretty repeatable. It's not perfect, but it was kind of neat. It's much easier to see this than to see, pieces of tape on the floor. With all the different things. Anyway, that's the video. This was the robot, the platform. It's a 22-inch motor, differential drive with a RoboClaw controller and an ESP32 board. And I was basically trying to see it. I'm steering it with a compass, and I'm also, when it moves, I give it a compass heading and a distance. Excuse me. So I wanted to see how well it was following that, and even, there's plenty of rebar in the floor here, so I thought that might screw it up or get it off a little bit, and it may have influenced it in some of these places, but for the most part, it was pretty good. I was pretty happy about that. I then went outside and tried it in the actual grass, and there's a flap on the back of it that was catching. I don't have very good grass. It's mostly these coarse weeds, and it was catching these weeds and preventing it from really moving that well. So what I've decided, I've wanted to build a 4-wheel drive platform, and I've made 4 of these. I basically welded a sprocket here to a hub, and so basically I have 4 drive wheels. This is just a fixed wheel. It's not a caster, and I'm going to decide on what mowing deck to put on it, because I've got a couple options, but I want to try to make it so the wheels are basically square around the frame. It's as far apart in one direction as they are in the other direction. And hopefully I'll get a lot more traction out of that. I've got some really wide wheels on the back of the mower. They're like 8 inches wide, and those provide enough traction, but that's Ackerman steering. It's not going to be, differential or skid steer type steering. And so that's where I want to move to, try to, get away from just 2 wheels, driving it, because the terrain out here is too rough. So I ordered a bunch of parts and, made those up, and hopefully it'll work good. So, but the steering with the compass, or actually moving, I used to just rotate to a compass heading and then use odometry, and assume that with a velocity PID loop on the 2 separate wheels, that it would go in a straight line. And that works really good on garage floors or indoors. Doesn't work very well at all outside, because there's just too many things that can, catch and throw it off. There's, varying terrain, there's weeds, rocks, you name it, they all throw it off a little bit. So odometry really isn't that useful on, at least, on rougher terrains. You always got to include a compass heading or guidance with a compass heading. So it's a velocity PID loop to a compass heading for a certain distance. So
Ray, which compass were you using? Were you using the B&O 55 or that Captain Jack Sparrow thing you had with the optical camera looking at a?
No, I was using the B&O 055.
Oh, okay.
No Captain Jack Sparrow's compass in this design. So.
Have you done anything further with that camera using computer vision on a physical compass? Have you done anything further with that, or was that just a fun exercise?
No, it it looks like it should be drift free though. It's like it's always going to follow the magnetic lines of the Earth. So, but yeah, so both of them they're basically mounted on an aluminum mass, and I've got it's the B&O 055, and then it's just a OLED display, so I can tell whether it's calibrated or not. And, if I shade the display with my hand in the bright sun, I can still read it. So, I can tell what the calibration is. So, but anyway, so that's where I'm at, heading towards 4-wheel drive platforms.
Cool. Progress on several fronts. Yeah.
Yep.
Very good. All right. So Kumar, what have you got this week? I've seen all kinds of email on the distribution list going back and forth.
I spend more time reading and emailing than doing. and everybody tells me, hey, you are a maker. What are you making? So I always have been fairly enamored by small itsy bitsy things. So what I want to show is I got a wireling basic kit, and I don't know whether others are aware of it, but this here is the kit. The main board is about 3 centimeters by 1 centimeter, and it has got these 5-pin connectors, so I don't need to do any soldering. And over here I have an OLED display, and I have a light sensor, and I also have a push button. So when I press this push button, the LED comes on, and this whole thing was $50, and within about half an hour, I was able to get this up and running. It runs on Arduino, so it's not like a Python kind of stuff. But the size of it is so small. These small boards here are each 1 centimeter by 1 centimeter, and you have all kinds of wirelings which are available. There is also, and I'll just show it on my screen in a minute, a robot kit based on this, where you can connect to motors with encoders. So when I said I like small things, no cabling, the other thing which I did is a QT Pi, and the QT Pi with a B&O 055 Stemma QT connector with an OLED display, also Stemma QT. So all you do is no wiring, 4-pin cables, connect one, but this one works Python, and this one is Arduino. And that's what finally I can say I made, and I did not send emails. So a couple of things which I did over here.
Can you say again?
What is the other board called again?
I can probably maybe a little bit of background is that the boards that Kumar's talking about, not the QT Py, but the other ones, come out of a company called Smart Prototyping, and they make PC boards and things out of Hong Kong, but they also sell several different lines of boards. They're the producer of the Zeo lines, the purple boards, like the Zeo Pi board. And among the lines of boards they sell are 2 or 3 different lines of boards, including these little 1 centimeter square boards that are all connected with a set of connectors. And so if you go to smartprototyping.com, it's is it smart?
The one which I bought, Murray, is this wireling basic kit.
Right.
And they also have something called a Robot Zero processor. And this is about like $50 again. And you can connect 2 drives and 4 servo motors. And you can have these stackable things over here as well. So these are not the Zeo. These are
they're not.
these are the wiring from Tiny Circuit. These are not the Z01
Oh,
which you
sorry.
mentioned. Yeah, that's what I had to show, nothing else. And compared to all the people who work with GPS and X2Go and very high precision, for me, my first maker in this forum is this small itsy bitsy thing.
Hey, I got an unrelated question for you, Kumar. What size micro SD card did you need or end up using for your Raspberry Pi to fit Ubuntu Mate and ROS on it?
So I had a Raspberry Pi 4 with 4 gig RAM, and you can actually fit it in 16 gig of SD card. But I had like a 128 gig SD card, so I didn't bother about space because I said,
Yeah, I'm
just have
I'm
whatever
using
you want and you
16
can
gigs on
expand it.
mine right now.
My
What's that?
apologies, Kumar. You're right. It was the Tiny Circuits company that has the 3 different lines. So tinyscircuits.com. They have a Tiny Duino, Wireling, and Tiny Lily. Yeah, that was the one.
Chris, can you repeat what you just said?
Can you actually hear me or something? Okay, I think you can, right? So yeah, I have 16 gigabytes as well to answer Paul's question. It's perfectly fine.
16 gig was enough.
16 gigs is enough for Ubuntu plus RAWs, and I have how much free right now? I'm using 60% of it, and yeah, it's plenty of space.
Great,
And
thank
Paul,
you.
in my case, I also installed RViz. So you can actually see the movement. RViz, the visualization tool on the Raspberry itself. It was not connected to an external system like a networked ROS. It was a single system ROS, including the visualization.
Thank you.
I had a question. I don't know if I should jump in with it or hold on, but I was kind of curious. There's been a lot of discussion, Kumar and Paul, and maybe others on anyway on GPS RTK, and I wonder for those that are setting up their own base station, what did you use for the radio link between the base station and the rover?
Probably something for Kareem to get back on.
I think Kareem is the only one here that can answer that.
Go ahead. Go ahead, Paul.
I did I'll just say that it was 2012 when I last ran RTK and did a ROS driver or ported a ROS driver for one of the new NavSpark, I think it was, boards that came out around that time. And they supplied I think it was called a 3D robotics radio that was popular in drones at the time to send the corrections from the base station. And then professionally, we always just used a network radio system between the robots and the base station. Go ahead, Kareem.
I love the name 3D Robotics Radio. I'm like, dude, hits all my points, right? So anyway, I'll shut up.
We were just playing with a 3DR drone radio. Those are both basically set up for telemetry, and they're not real high speed, or they're not high bandwidth, but they're plenty to send the correction packets over. But we haven't ever used them for actual RTCM messages. We've been using RTK to go. So when I set up a base station, like I went on vacation in South Padre and I set up a base station down there, but connected it through rtk2go.com and published it through Intrip. So you could access it from any internet browser or any internet connected robot.
So Kareem, those are the videos you showed us down on the beach?
Yes. I was using it when I think I I'm not sure what I showed back then. Um, but I was doing experiments on the, every year that we'd go to the beach, we skipped this year. We always have some sort of robot there and doing some kind of experiments, trying not to drive into the sea.
So Karim, one question. If I have a rover and that rover is in my backyard, and I know that even if this RTK to go is not there, just from the satellites, I can get it to 1 meter accuracy. Now, that is absolute accuracy. So if I want to move from one location to another place in my backyard, even though it is 1 meter accurate, once you measure it, the relative distance when you move to the next location, you should be able to move, say, 10 centimeters, 100 centimeters. And that, no, so the
No,
accuracy is so
that
so
is not
from
how it
from that
works.
from
Yeah.
that rover, can I, if somebody has got an NT-RIP server and there is an RTK to give, so can I go through the internet to that particular position and get that information on a $30 GPS device, or do I need the $275 device on my rover?
You need the expensive RTK receiver on your rover. The one that's at the base station is also going to be an expensive. It's not a standard GPS unit. There, it's resolving some very fine-grained timing signals to sort of correct, stratospheric perturbations in the signals, right? So that's one of the reasons you need it to be sort of within the same region, because it's sort of characterizing the atmospheric effects of the area that you're in and correcting for that. But it doesn't have to be like, within 30 feet or anything like that. It just needs to be in the general area where you're operating your real-time kinematic receiver.
Yeah, but what wasn't he just describing differential GPS, which I know it's not the same thing, but it's close. It's the same. The underlying idea is the same.
If you're talking 1 meter, then yeah, you're probably talking about differential GPS, and there are different kinds of correcting signals that are involved with that. I don't know if the unit that you posted from Adafruit has differential GPS or not. That's definitely more affordable than the RTK stuff.
Does anyone know where, if it's possible to find the latitude, longitude of Army Corps of Engineers survey markers? Because I've got one at the bottom of my yard, and I was looking on the web and I couldn't find like anything comparable to the NGS, in National Geographic Service dictionary of markers. Does anyone know of how to find the survey position of the marker?
Paul, isn't it on the marker?
It's what?
Isn't it on the marker?
No, the marker.
The marker won't show the actual GPS location on it.
It just shows the marker just shows like a reference number, and those are northing and easting. They're not latitude and longitude. They're north and east of a reference point. And I know at SMU we've got several of those around campus, and I've used them. And somebody at SMU was able to tell me exactly what their locations were. I can try to dig that up and find out how they knew.
But David, don't they not put the lat longs on the markers because the markers are actually moving? Like in California, there's certain places that are moving like, inches per year.
I don't think we have that problem in Texas.
Oh, really? No movement of ground, eh?
Well, at least as long as we're
slower.
not doing all that shale injection and all that kind of stuff for a while. Take a little bit for that.
Yeah, I'm not sure if it's a New Zealand term, but you guys know what a trig is at the top of a hill or a mountain? A trig point? It's like in New Zealand, if you go tramping or backpacking up in the mountains, there's these kind of constructions they put up that have kind of they don't have any electronics. They're just kind of a marker, a visual marker, and they're called a trig point. And they'll be on the tops of all the hills and things. And the trig points are constantly moving here. Like, they don't have a fixed location. That everything in this whole island is moving relatively rapidly, actually. So there's no point in printing anything on anything around here. So, but Texas is much more.
Even here, those markers just have an ID number, and there's different authorities for different versions of those. So there's a lot of private one, not necessarily, yeah, even private ones. So sometimes just surveyors will sync a marker, but I haven't found an authoritative source for all of the different kinds. We moved recently, and so the markers that when we got the survey for our new property, it did include the markers that were on the property, and I was able to look up through City of Dallas database the northern and easting kinds of stuff. But I actually paid the company to land a GS marker as well. So I knew exactly where it was, and they resolved it with GPS RTK. But based on that, I can set up my own base station once I get around to it. I just haven't had a need to.
You know, Kareem, that's a good point. Probably the reason they have those at SMU is that their own engineers use them for laying out the buildings and such.
Right. Yep.
So those may or may not be Corps of Engineer markers.
But they may be even moving relative to each other. Like in my house, I've got a 1/4 acre roughly, and there's 4 markers, of course, for the property boundaries. And the one that's in the northeast corner has moved, I think, over a meter since my house was built. And
wow.
Well, that's because my house is on the edge of a ravine or a reserve, and the whole hillside's gradually moving downhill. And so I've got 3 24-inch concrete stormwater drain pipes that are now anywhere from 1 meter to 1.5 meters apart from each other, with the one that's near that corner actually now at an angle like this under the ground. So things do move even when there's not earthquakes.
So I just put a link in the chat from it's this magazine I've been getting ever since I sort of tried to work for a drone startup for a little bit, and I've been getting this free subscription ever since. But it's basically for geospatial professionals, and I seem to remember an article a couple of years ago in there that was about this, or something similar. Apparently, there are these really durable, substantial markers placed around the world, or at least around the United States, that the Corps of Engineers dropped in the 50s or something. And every now and then somebody stumbles on one and wonders, what in the world is it? And it turns out that it's one of these that's it's just meant to be a really substantial, as I remember it, a really substantial location marker so that they can calibrate things.
Well, I remember decades ago when I was in my actually late teens, I think, living in Alexandria, Louisiana. We'd go down to the Red River and then explore through the woods, and I found one of those markers. It just like a little brass marker about 3 inches in diameter, a little, I guess, and some numbers on it, and we eventually figured out that's what it was.
Yeah,
we've got.
So I've seen one of those on the border from between Canada and the U.S. on the Canadian side, and like you say, it's got a brass marker plate at the top, about 3 inches in diameter, and it's a concrete structure, and it's round, smooth, and it drops into the ground. I believe it's about 20 feet underground. So it's sticking up 3 or 4 feet above the ground, and I believe there's another 15 feet below the ground or so.
Yeah, serious
I've got
anchor.
4 of those. I got 4 of those on my property, but they're not elevated. So a lot of the official ones are elevated, like if they're beside a highway or something like that. But I've got 4 that are sort of flat with the ground, but they're also got an iron pipe underneath on purpose so that you can sense it, with metal detectors as well.
So Pat, when you cross that marker, do it during the day, because there's that clearing area that's on the border there. You'll be really exposed.
No, I was about 1,500 feet on the Canadian side. It's well on both sides of the river, from Sault Ste. Marie, Michigan, and Sault Ste. Marie, Ontario, and It's just a position to mark how far away it is, basically, from the not the continental divide, but the Canada-U.S. border.
Yep. Yeah, on the western side, God, I don't know exactly where we crossed now. It's been a while, but yeah, there was like a clearing that went like straight up the side of the hill and wasn't very wide. So I'm guessing, you know, if you really wanted to cross, you could. So
it's the Canada-U.S. border. When I was a kid, when I was a teenager, well, older than that, near 20-some years old, we took a 14-foot aluminum boat and we rowed across the St. Mary's River and camped out on the other side of the beach. And, you know, we never declared anything, including the beer or that we were in the U.S. or, you know, any of that. And it was that was the first time actually I ever went boating downhill.
No statute of limitations on invasions.
Yeah, exactly. There was a ship that had crossed going into Lake Superior in front of us. And as we were driving towards the south, towards the Michigan shore, we were going actually up the wake from the boat. We were boating uphill. And when we crested and we started going downhill, that's when we said, oh, poop. Because now you're going downhill at about a 30-degree angle in the wake of this 1,000-foot freighter that just went by. We were lucky we didn't end up in the bottom of the river. The boat was flooded. It just about sank. Everything we owned was it got basically soaked. It was fun. It was an experience. I'd never been boating downhill before that.
I just wanted to show this here. I ordered one of these. This is what Spark Funds suggested, and I ordered it like August 3rd. They actually said at that point that they had some in stock, and this is what they suggested as the radio link between either there's two different module sets that you can buy, and this was the radio link. It's 100 milliwatt. It's a 915 megahertz, but it doesn't say it's LoRa. So I'm assuming it's the non-LoRa, that's in that ISM band. Anyway, they still haven't gotten any in. I don't think they're going to at this point. They said that that you could try to use LoRa, and I used two of the ESP32 modules with the lowest number of chirps and basically the highest speed, least reliable transmission method. And I actually got it to RTK float. It didn't go beyond float, but I hadn't let it sit there for very long. So, maybe I think it was actually about a half an hour that it sat there, and it would go to RTK. I guess float is the first one and fixed is the second one. Isn't that right? Yeah. So it looked like it worked. And I was going to suggest that if anybody else is, looking for what to use, you can try LoRa transceivers. They seem to work.
Right. Those radios you're showing are similar to the ones that Kareem was talking about, the 3D drone radios. I've got,
they are.
They also went out with Autopilot and Pickhawks and all of the other drones.
Mm-hmm.
Yeah, they work pretty nicely, but they're somewhat comparable to LoRa.
Yeah. I know. I think Murray was using some 950. I think they were 915 megahertz, or maybe they were 433s. I don't know, but similar, right?
Yeah, they're they're called the RFM 69s, and they're software settable. So you, depending on where you are and what's legal and all that, you can set them for 868 and 915 or something like that, or you choose a different board that's 433 megahertz. But you have to obviously have both both of the transceivers at the same frequency and the same style of board. But
Yeah.
I've got the RFM69 ones, which are supposed to be easier than LoRa to use, by the way.
Okay.
Cool.
Anyway, I tried setting it up at my house because I'm nowhere near, you know, a location that I can use. So, but like I said, I got it to RTK float, I think, or whatever the first higher resolution, you know, GPS RTK is. It never did go to fix, so I'm not like, maybe I needed to let the base station sit there for like, I just did like 5 minutes, and it was, I think, 5 minutes and less than a meter and a half accuracy. So probably if I let it sit there much longer, it would,
Do you
it would
have
have been better.
L1 and L2 or only L1?
I forget what those modules will do. I think it's both, because they'll do.
Okay, because L1, my experience was that single frequency can take like 20 minutes to go to fixed, but the dual frequency ones are supposed to go to fixed, lock onto fixed in about 30 seconds.
Oh, that quick! Wow.
That's typically what I get, unless there's some weird atmospheric conditions going on. Usually it'll resolve pretty quickly if you got a decent number of satellites in view.
So like 20 minutes then.
Huh? No? What? 30 seconds.
Oh, 30 seconds.
Yeah.
Oh, wow.
Wait, so wait,
fast
you might be
fix.
talking about something different. You may be talking about getting a fix for your base station.
Yes.
Okay. No, that should take a while. Sometimes people will let them go for a couple of hours to really settle in. If you're using survey in
Yeah.
to do that,
Right.
then you want to give it some time to do that. But once your base station is well fixed, then your rover should fix to beyond float. It should go to RTK fixed pretty rapidly.
Fixed. Okay. Yeah. Yeah, I just did, you know, whatever it was, 300 seconds, 5 minutes, and you know, down to better than 1.5 meters for the base station, but never let it just sit there long, you know, much longer than that.
Yeah, you want to get that base station pretty well fixed, right? Because
Yeah.
the accuracy of your rover is going to depend on that. And that
Right.
possibly is what's the issue with getting beyond float. I'm not sure.
Okay. Yeah, that's what I thought. Anyway, we live so far apart from each other. Maybe, you know, we can find the person that's the most centrally located, have them set up a base station.
Well, that station in Richardson has been pretty good. When we moved to far south Dallas, and so now I'm about 32 kilometers away from that one that I referenced in my notes, and we're still using it, and it's still working just fine. So you can get pretty far away.
Really? Okay.
Yeah. They always talk about 10 kilometers as the desired maximum, but look up. You can just search on long baseline RTK, and there are a lot of experiments out there done on it. And I've seen people advertising that they've been able to go up to close to 75 kilometers and still be able to get a really high quality fix.
Yeah, I guess what 10K is only like 6.2 miles, right?
Yeah, that's pretty tight, and that tends to be the recommended distance still in like all of the literature, but you can't go beyond it. It may be a regional thing, right? Maybe because it's flat enough here in North Texas to not matter that much. I don't know.
Okay.
All right. Cool. Well, I think we have next Mr. David Anderson, and then me, and then I don't know if anyone else wants to go after that, but okay, good. Chris will after me. Okay, so with that, Mr. Dave, what do you got? Audio.
Mute.
It says, "Are you talking? Your mic is off."
Oh, it knew.
Basically, I was sort of inspired by what Doug had done, and also by Chris's talk last weekend. He had this really brilliant demo of using LiDAR to correct his drift in odometry, and which also had some other advantages. It lets you square up with the room sort of automatically, and pretty cool. And so I was thinking about this and thinking about the discussions we'd had about navigating. And I just, so I shot some video, but before I show it, I want to pontificate, if you guys will allow me. I had mentioned in my talk last June that sort of the father of modern navigation is a guy named Nathaniel Bowditch. He's an American who lived, I think he was born about the time of the Revolution. And he's a mathematician, and you can look him up. He's a pretty interesting guy. But and he sort of developed, and he wrote the textbook that all the navigators carry on their ships now. I mean, it's pretty cool stuff. And there's a famous story about Nathaniel Bowditch on a ship. It was actually his last, I think his last voyage. So this is about 1802 or something like that. Coming back to Nantucket, and there's a heavy snowstorm and heavy fog. And so nobody could get into the harbor. And so what he did was he did what nowadays we'd call dead reckoning. He was confident in the fix that he had, so he knew where he was. And then he would set a compass heading, tell the helmsman to hold that compass heading, and then they have a guy with a rope and a log. They throw the log into the water and see how long it takes to drift from one end of the ship to the other. You're using the ship as your fiducial reference to know how fast you're going. And using this, he would calculate an angle and a distance, and then they would try to sail that angle and distance, and then he'd calculate a new angle and distance. And they actually made it into the port. You know, this is at a time when these huge sailing vessels were going back and forth, plying trade between across the Atlantic, and there was a lot of money on the line. So if you could get into port, you know, without having to wait out a snowstorm for a couple of days, you had a huge economic advantage. And of course, everybody else immediately copied that. And if you get a chance, look up Nathaniel Bowditch. He's a pretty fascinating guy. Okay, so that's my preface. So basically what he's doing in Dead Reckoning is he's making a calculation at the beginning of each run. What should my angle be and what should the distance be? And then in the terminology that we used last week, he does what we would call a ballistic maneuver. That is, he tries to turn at that angle and tries to go that distance. Then you know, if you had the luxury, you'd take another reading at that point, but they didn't. So that's like us. So then he goes to a new angle. Modern ships, like the one my son is a navigator on, don't work that way at all. What they have, you know, they have computers controlling the rudders and the pods and so forth, and they're constantly calculating the heading and distance to the waypoint, to the target. And so there's a control loop, and we were talking about this before we started, an actual PID control loop that runs this so that you're constantly at whatever update rate, you're constantly correcting the rudder or the thruster pods or whatever to keep the boat pointed toward the waypoint. Carl, in the terminology of the post you put up here a couple of days ago, the boat's trying to keep the waypoint in front of it. So you're not just sailing in a straight line. As a matter of fact, it might not be in a straight line. What you're trying to do is trying to keep the waypoint in front of you. Yeah. And so it's if you compare what Bowditch was doing, and as I say, that you can think of that as a ballistic behavior. That is, he rotates a certain amount and he goes forward a certain distance. And you compare that to the sort of ships my son is on, they use what we call a servo behavior in our terminology next week. That is, or last week, that is that they're constantly correcting the heading in real time, rather than making a single calculation, executing it, making another calculation, and executing it. So if you bring this forward to what we've been doing and what we've been talking about, basically, and Doug, that's why I wanted you to hear, correct me if I'm wrong, the excellent demo Doug gave us last week was basically a demo of dead reckoning. That is, he picks a waypoint, he rotates toward that waypoint, and then drives toward that waypoint for a certain period of time. If there's an obstacle in the way, on the way, then he calculates a new waypoint, a temporary waypoint, rotates toward that waypoint, and drives that distance. So basically, at each waypoint, you're doing the calculation once, and then you wait to get to the next waypoint, and you do the calculation again. So that's kind of how Bowditch did it back in the 1700s. But the way the
a little different.
Oh, well,
yeah, but I think you're right. I think it's a matter of time. All right, like he was waiting for the log to go all the way down the length of the ship. And I'm sure that took at least 30 seconds, right, before him to get a new waypoint.
No, the log going down, he doesn't get a new waypoint. The log going along the side of the ship is just how he gets his velocity.
Mm-hmm.
So he's going to use velocity, and he's going to use a compass, and then he's going to try to get to the next waypoint.
So the way I'm doing it, and you tell me if this is the same. All right, I have a waypoint, an end waypoint. All right, and I'm trying to go to that waypoint. Whenever there is an obstacle, okay, then I make a temporary waypoint. Now, that distance for that temporary waypoint was, I don't know, 2 feet or something like that. You very rarely do get to that waypoint because you're constantly looking for obstacles. So in my case, I think it had to have 5 in a row. See an obstacle 5 in a row. My sample times are like 20 milliseconds. So what is that, 100 milliseconds? Every 100 milliseconds, it assesses 2 things. Do I have a new obstacle, or am I still going on the path from my previous obstacle? Okay, now, if there's no obstacle, let's say I turned for my first obstacle, and there's no obstacle in front of me, then it will go to the temporary waypoint before it tries to correct. All right. Now, if it was mentioned, well, why don't you just turn until you don't see a waypoint? Well, I could stop
until you don't see an obstacle.
Right. So I could do that by simply making the target waypoint. Otherwise, I have what I call a detour distance and a detour angle, which are set at the temporary waypoint. I could make them very small, okay? And it would just, every 100 milliseconds, it would go toot, 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 until it didn't see it, and then it would have to go some distance. But the problem is it would be constantly looking to try to turn back to home, okay? Because as soon as you don't see an obstacle, if you don't have some sort of movement in time, the robot on the next cycle is going to say, well, the temporary waypoint has been reached, so I'm going back to my original waypoint, and it's going to turn towards the original waypoint. So that's what I'm doing. Now,
right. I think that's as I understood it.
Yeah.
And basically what I was trying to get you to sign off on was me using the term ballistic to describe dead reckoning. You're doing a series of ballistic maneuvers.
The maneuver is ballistic, but it doesn't necessarily ever come to fruition. So it's extremely interruptible. I guess that's the word.
Yeah.
It's an interruptible ballistic. And now that's because I'm doing this on a fairly crude, I'm setting a distance and an angle. But, I could get slick and make those angles depend on other functions, maybe all of the different sensor suite, whatever.
Phase of the moon.
Yeah. So,
but isn't Isn't your odometry servo behavior, right? Because you're constantly
Odometry is
measuring
just
two
a
different.
sensor. It's not a behavior. Right?
I know, but he's steering based on the changes to the odometry.
Well, I would ask him this. If I go from my starting position to my waypoint, is that a ballistic behavior?
Well, it could be done in different ways. I was trying to.
No, but I'm just saying, if I have no obstacles and I start
Yes.
off and I drive to my way, that's a ballistic behavior.
Yeah, I would say that your ballistic behavior had two parts. The first part was it ballistically rotates to a certain angle. And the second part is that it then drives in a straight line a certain distance. So, for example, the kind of ship that I was referring to that my son is on, modern ship, since it's constantly correcting to keep the boat going to the right point. So if the ship,
okay, I'm sorry, Dick, go ahead.
If the ship gets shoved sideways by a wave or something, you don't have to recalculate a new waypoint because
I bet they are.
The system is no.
Oh, I bet they are. Yeah, sure. They've got a fixed position they're supposed to be at, and they're coming off of it. So they create a vector saying, I need to go back to this position that I was at. That's just a waypoint.
I'm not going to get into that, but that's not how it works at all. I can guarantee you.
Okay.
I learned a lot about navigation this week talking to my son. I now know the difference between the celestial horizon and the visual horizon, and that they're about 0.7 degrees apart.
Okay.
All right.
So
I wanted to set that as a preference before I showed these videos so that I could try to.
But what I'm going to say, in my idea of a ballistic behavior, does have because does have this conception that it isn't interruptible. Now you can argue, well, I won't say this, but I will go ahead. Say a ballistic missile, but obviously that's interruptible. I mean, you can always destroy the missile, So, but the intent was that once it runs out of fuel, it just drops ballistically. All right, and if you didn't intervene, it would be a ballistic. So I think that you either have to say there's interruptible ballistic behaviors that, like I say, that are in a different class, and then there's ballistic behaviors. For example, if you back up for 1 second, that's a ballistic behavior because you're not interrupting it during the 1 second. All right. Now, if you had a sensor on the back of it and you started backing up for your 1 second, and all of a sudden you saw something and you stopped,
well, Kumar,
is that a ballistic?
Oh, you ran him off.
Yeah.
So anyway, success.
Okay.
Well, I don't want to get into the vagaries of definitions of words.
Okay.
The ballistic behaviors that run on my robots, for example, to rotate at a stop to rotate through a certain angle. If while it's rotating through that angle, it hits something, then that behavior aborts. The bumper behavior aborts that behavior. So, but the idea that the difference between a ballistic and a servo behavior is not whether or not they can be interrupted. It's how they're controlled. The ballistic behavior, once you set it in motion, there's no more calculation involved in its control. Whereas a servo behavior, which we're all familiar with, is like line following. When line's left, you turn right. When it's right, you turn left. And the behavior, behavior is a real-time behavior. However, I want to jump into my videos.
Go ahead.
So that video.
Okay, so what I attempted to do was to replicate what, Doug, what you did last week. And let's see, what do I have to do here? Present your entire screen, select window or screen, entire screen, allow. Did I do it?
Coming up.
Yep, something's coming up.
Do you see a
Yes,
little
yes.
room with some yellow lines on the floor?
Mhm.
This is the old messy basement where I used to enjoy running my robot so much because there was so much crap. But now they spent a lot of money and made it real useful for humans and just totally useless for robots. It's really sad. Okay, you can see I've got a little piece of black tape down there And so here is Doug's demo number 1. And I'm going to stop as we go through this. So we're driving in a straight line toward our target waypoint. And when we get there, we slow down and stop. Stop. Now, the robot, let me do that again. The robot's actually not driving a certain distance. Rather, it's steering toward, it's not driving in a straight line. It's steering toward the straight line. If you watch the tail wheel, you can see little corrections it's making. And then when it gets within a certain distance of the waypoint, it uses the distance to control the velocity. It slows down and stops. Okay. Now, Doug, I have to encourage you here. For 5,000 years of human navigation, the main reason to navigate is so you can get back home. That's the whole purpose of navigation, is to be able to get back home. So it's not enough to go to, if you're doing a waypoint route, that would be different. But for any kind of test, the test is not complete until you get back home. You don't really know if your navigation is working unless you can get back home. So
I agree. So that's a good challenge, and I'll accept that. I'll go to a single waypoint in the other room where it has to do a lot of wiggly, and then I'll make it come back and go to the original spot.
You make to the edge. So
Yeah.
okay, so when as I've described before, the navigation behavior is the lowest priority behavior, and so when
I want to do mention mine is all under PID, is an angle control too. You know, mine's when it's turning to an angle and starts to move, it's also oscillating slightly around the heading as it corrects. You know,
but the oscillation I'm talking, well, I'll get
that's
back.
that's just your outer PID loop.
So at this point, the navigation behavior, which is the lowest priority behavior, triggers a high priority behavior, which is a ballistic behavior, and that ballistic behavior rotates through a certain angle, and the angle it's being given is the angle it's required to point to the next waypoint. So at this point, the low-level behavior is subsumed by a higher-level behavior that rotates toward the waypoint. Then the navigation takes back over again with the new waypoint and attempts to rotate it toward it. So as I say, to do long treks and so forth doesn't make any difference, but if you're testing the thing, you really need to see that you've gotten back to the origin. Okay, so that was test number 1. Okay, here's number 2. We have an obstacle, and I'm going to stop it again so I can jabber along the way. So the same thing, the robot's attempting to go from here to that piece of tape. It doesn't know that there's an obstacle there or anything about its environment. It's just trying to drive in a straight line, and it drives in a straight line until it gets right there. At that point, I don't think I have the sonar turned on, so this is just IR. But you can see that the left-looking IR is looking out here in space. The right-looking IR sees the box. And so we begin to turn. And it continues to turn, not for a specific angle, nor for a specific period of time, but until it no longer sees the box. Mm-hmm. So right there, I don't know if you can see this side-looking, this side-looking IR right here can still see the box. Yeah, right there, it's looking right at it. So we can't release control of the robot. That is, this higher level avoidance behavior can't release control of the robot until the box is clear. So we drive a little further, and right there, you can see we're totally clear of the box. We can't see it anymore. At that time, the robot times out basically after about a quarter of a second and releases control of the robot. And so the low level navigation behavior takes back control and steers it back toward the robot. So that's where that curve came from. Because we're calculating not once what the angle to the target is, but we're calculating it on this robot every 40 milliseconds. So 20.
Oh no. Froze.
I think
he lost it. Well,
I think he's gone.
I see
Video's
the video.
playing.
He's coming back, I'm sure.
Internet
Here,
hiccup. Several people dropped and then.
Oh my goodness. Google Meet, what is going on? They're pulling a Zoom.
Hopefully it doesn't pull a Facebook and it's down for 5 hours.
You know, that would be bad. David, we can see your mouse and assume you're talking, but we can't hear a word you're saying. Don't know if you can hear us or not, but we've lost you, David.
Hey, Carl, can you, well, it looks like you dropped out. Okay.
Yes.
I'll come back.
You'll be back. Yeah.
You'll be back.
You'll be back.
Okay, while we wait, so after David, we have me and then Chris. Does anyone want to jump in after Chris?
I have a little something, but it's just
K.
a little bit after
Yeah, I
John.
could show something while we're waiting for him to come back if you want me to show you real fast.
You got a fast one. Why not jump in?
Is it intermission length?
There's no telling how long it'll take him to reattach.
Cancel on one. I was surfing, you know me, I tend to like rear things a little bit, so I saw this. So it has a different type of movement, which is interesting. So it's a real must skip a robot. And they actually have video. So let me see if I can get to the video somewhere here. It's sort of interesting how it moves about. So it's very much like the fish.
It's cute.
One of the mud skippers.
Yeah.
Yeah. Yeah, that's what it sounds like.
Bypass this part. Get back. Let's see. Okay. So he has it where you can do a remote, but yeah, it basically lifts up and moves a little bit. So it's very much like the fish. So I thought that was an interesting way to move about.
It's basically oaring, isn't it?
Yeah, it's basically lifts up, moves a little, and then moves. So I thought that was interesting. It's very much like the fish. And then the other thing, was the inchworm. So this one's a little bigger in the sense that it actually has a head and tail there. And in the middle is how it basically can go different angles. So I thought that was an interesting way to do it. So I don't know if that one could be enlarged, but but it's an interesting thought. Of the two, this one's probably more useful. So those were the two things I saw that was of interest. So
cool.
So that's
Okay, very cool. Just a second. I'm trying to get links up in the chat here for us, and get David a little bit more time.
a little too fast, huh? Okay.
Yeah. Let me text him and see if we can't get him quickly. Let me see, David. Oh, I don't have his phone. I only have his email. One more second here. Let me check this out. And then meanwhile, okay, I had a precondition that I wanted to show David what I was going to show. Chris, do you have precondition on what you want to show?
Mute.
Got it. Yes, thank you. No, I can go. I'll need, I don't know, 10 minutes.
Okay. 10 minutes to get ready or 10 minutes to show?
No, 10 minutes to show, whatever.
Okay.
I'm ready.
Well, let's
Okay.
let's go ahead with you then, and while we wait for David, I sent him an email.
Okay. All right. So let me then switch to sharing, and I turned my second screen off because last time it wouldn't let me pick which screen. Okay. So let's see. So now, all right, you don't want that. Okay, just another installment of my adventures in setting up RAWs on my Romy platform. So I'll just show a couple of the visualization things that RAWs can do for those who haven't seen it in action, and sort of where I'm at with navigation and kind of working towards that use case from Doug. Well, you go from here to there, there's some obstacles along the way, and you come back. So right now it's sitting here right next to me on sort of where I have it plugged in for charging, and the arrow represents where it thinks it is right now. And I'm just going to turn that off, and it's actually not that sure right now where it's at. If I turn off a different view, this is from the particle filter that's doing the localization. It's got particles all over the place pointing in all kinds of directions. It's just kind of a way of saying, hey, I think I'm there in the center of this cloud, but I'm not sure exactly where I'm at. Or here's another way it can show that, the circle, it's somewhere in there, and then the yellow cone as well. My heading is somewhere within that cone. Okay, so it's because I've moved it around, and so it's not actually that well localized right now. I'm doing something a little different than last time. Last time, what I was showing, and I was doing just a playback of recorded data last time. This is live data, but last time I was showing the scenario where you're doing the mapping and the localization at the same time. What's going on here right now is actually just localization. So it's using a map that I've built previously, and I've just turned that on for visualization purposes. So I've built the map previously, and you can see it's not it's not a terribly good map of my heavily cluttered office up there, and then some hallways there, and it's using that map right now for localization. So again, I'm in this kind of use case that I'm exercising here. I'm not building a map, I'm just assuming there's one given to me. And for the things I'm usually doing, it's a good assumption to make. I know what the basic parameters are of where I'm operating. I have a rough map. It doesn't have to be super accurate, but I know where the walls are. I know I can't go through the walls, so I'm just giving it that information basically.
Hey, Chris.
Yeah.
I'm assuming you have the door closed and you didn't have
That
it
is
closed before.
that good observation. Yes, right now I have the door closed exactly, and that's what the laser is picking up there in the map. Well, I had it open, and it might interfere with localization slightly, but not too much, right?
Okay.
So that's what's happening right now. It's localizing, given the map and giving the laser. Now I'm going to attempt to move it. I'm going to have to unplug it from charging. I'm going to move it to what I usually use as the starting point. If you can see my mouse, it's going to go over there. And let's see if I don't lose anything in the process. But I'm going to unplug the robot, move it, and obviously my wheels are not turning, but my IMU is still functioning. So it knows it's getting moved because of my IMU, even though my odometry is not giving any clicks. Okay, and it's way off. So there's one way I can now help it relocalize itself. One is to actually move it around a little bit, and then it picks up enough data to localize. But I'm not set up with the joystick right now, so I have to do something different. I have to give it a hint and say, you know what, you're here, somewhere here, pointing in that direction. Just make that assumption. So I just told it where it's at. Okay, that's what I did. I'm not set up to tell it to rotate in place or something. It would have figured out where it's at. So you're just gonna have to trust me on that one. I'll demo that some other time. But so I just had to help it along, telling it, you know what, this is where you're at. You know, it still assumes a bit of a uncertainty here, and it's letting me know that it's not that certain. So now, getting more into the actual navigation part, what I wanted to show is, okay, I wanted to go from here from point A to point B, using basically some of the built-in RAW's features. So now I'm just going to turn the global map off because it's visually distracting. But what I'm turning on now is what's called the cost map that it builds, and it doesn't need the global map for that. It's just using the live sensor data for that right now, and you know, it's visualizing it a certain way. And what that really is saying is, you know, these colored areas, you can't go there. You know, and different colors mean, you know, kind of lethality of going there, right? It's sort of the way the colors work. I guess it's the blue. Yeah, it's okay to still be there. Let's try to avoid it, you know. But once you get to where the laser is, and I can turn the laser off so it's not confusing things. Once you get into that magenta kind of area, that's kind of lethal. There's an actual obstacle there. You can't go there. And turquoise is, you know, you want to stay out of there for sure, and so on, right? So different colors mean different things. You're basically trying to stay away from those colored areas. So what that really is doing is, again, it's using the sensor data to build up this cost map. Again, this is a dynamic map. This is not, has nothing to do with this map of my room. This is strictly based on the sensor data. There is another version of it hidden in another layer where it does something similar, you know, with the static map. The navigation uses the static map I give it to kind of also, you know, maintain a notion of how costly is it to go from here to there, and it's infinitely costly to go through a wall. So that information is captured here too in another layer, but I'm not going to show that now because it's sort of more interesting to look at the live data. And it's right now the only thing I have wired up, well, or I shouldn't say wired up, but published, you know, in RAW's terminology, is the LiDAR data. I really still have to get to hook up the, not hook up, but software-wise hook up the sonar and the infrared, because the LiDAR won't pick up anything. I have some black leather bag on the floor. The LiDAR does not see the bag, you know, so that sort of thing. So one of the nice things that ROS lets you do, again, I still have to do it, and we'll see how easy that is, but I can tell it a little bit of metadata about my sonar, you know, where it's located on the robot, which direction it's facing, and it'll then incorporate the information from my sonar and from my sharp IR into this same cost map. Okay, it's kind of, look at it at sensor fusion amount. It's not really sensor fusion. It's just aggregating information from different sensors, you know, into this cost map thing, right? That it can use then to sort of navigate, or that I can use to build my own, you know, navigation algorithm. That's where, you know, it becomes really powerful, right? Because now you have this really powerful data structures that maintain this kind of rich information for you, and that you can then work with and come up with a logic that's actually using this. So, all right. So right now it's sitting there. Let me just going to turn this map back on so I know where we're at. So this is me moving around here in my chair. You can see the blob moving a little bit. I'm going to tell it now to move to down here. And this is again in the UI. There's a way to do that. I'll tell it to go from to there. And the orange line is the global plan. The green line, it's a very thin line, is what's called the local plan. And what it's basically doing is it's the orange plan is just a real high level way of getting from here to there. It only knows about the global map that I give it, so it's doing a straight line. And the green line then is really the one where it's dealing with obstacles along the way. And this was obviously no challenge. It just went from here to there. There's still a lot of quirkiness going on. It doesn't move in as efficient a manner as I think it should. So I gotta still tweak some parameters and try out a couple different alternatives to that same sort of concept that are available. So it's moving in a little quirky fashion. It's not, it's not that terribly, smart yet, so to speak. But let's make it a little more challenging. So I'm going to move it a little bit further away, just so I have a little bit more room. And it's moving very slowly right now because it's so close to the goal. And I told it doesn't have to hit the goal precisely, so I gave it some wiggle room. But for example, I don't know why it's like literally moving just super slow. Okay, it's finished. So now what I'm going to do, so now let's make it a little more interesting. I'm going to now ask it to sort of come back here. Again, I'm doing all this interactively right now, but you could imagine writing an actual control logic, right, where you are sort of issuing commands that say, hey, go to point A, go to this point in space, X, Y, and the following heading, right? I could issue those commands programmatically. I'm just doing it all interactively right now for demo's sake and kind of debugging sake. So I'm going to tell it to basically come back, but then I'm going to get in the way, right? And you'll see my, you'll see something like this going on. That's me standing there in its way. So I'm going to do that in a moment, and let's see if it can figure out dynamically how to get around me. It's not that good yet at getting around things. It's still crashing into things. Like I said, it's a lot more tuning to do, but let's see. You know what? I'm going to send it onto my desk here. That's what I'm going to do, all the way up here. So off it goes. It plotted a plan that's, actually there's too much clutter in the way that it can't see. So I'm going to get in its way now. Standing here, it's in its way. All right, so it can't go. You can see the orange line, right? It can't go there. So now it's turning around. It's trying to figure out, okay, where can I actually go? I have to help it along a little bit because there's clutter on the floor that it can't see. It's still trying this path. Haven't given up yet. Oh, let's see. Maybe I made it too hard. Yeah, I think I may have made it too hard. Let's see. All right, now it's making a bigger circle around it. Okay, I'm not doing anything here. This is just the built-in navigation doing its thing. So now it found another way. And you see the green line, that's the local planner, right? Trying to want to go back to where the orange line is, and ultimately the end goal. And so it eventually found sort of this opening in space here. After some tries that were a little more clumsy than I think they ought to be, but it eventually made it. And so that's kind of the idea of the navigation stack, where you have these building blocks that once you wire them up, so to speak, give them all the information they need, and give them the commands, to do something. It'll actually issue the commands to your motors, the velocity commands, for your motors, and it'll get you from point A to point B. And again, if you did this programmatically, right, then I could say go to point A. Okay, now come back, right? I mean, right now I have to do it interactively, but you can imagine a control logic sort of sitting somewhere behind here, and actually issuing these, destination commands, and it'll go there. And if it can't reach the destination, it'll tell you so, right? It'll tell you that, hey, I couldn't get there. I couldn't find an opening anywhere. Couldn't find a path. So so that's where I'm at. It's still very clumsy and still lacking. It's still not utilizing the information from the sonars, which in my cluttered space here is actually going to be quite critical. And I'm looking forward to seeing, how well it works with the sonar and the IR data. It knows that's different data. It knows that it has to treat it differently. It's not treating it just like a reading from a laser scanner. So this building block that I'm using here, knows that sonar and the simple IR sensors are slightly different and that it has to treat them differently, that there's more error in there and so on. But I've never seen that in action, so I really want to wire that up software-wise to see, what happens when you have that hooked up, because again, the laser right now is, as I said, is certainly missing a few things. Some things that are below the laser, and some things that are too black for the laser, and so on. So I have to occasionally help it a little bit right now. But yeah, so that's where I'm at. And what I also want to do is, because not everybody's interested in these use cases where you have a map or you're building a map. In principle, you can do all of this without this global map, right? With just the dynamic data. It gets actually a little bit more difficult because it's not in RAW's land, not sort of the standard use case. So doing all of this without this, a priori map given, it gets actually just a little bit more tricky. If you don't know your way around RAWs, as well. And so I need to figure that out. I think I sort of know how to do that. But then that would be a use case where I don't need to give it any map. Maybe I don't care about building on the map. I just want to navigate around in this random unknown terrain. And I just don't want to bump into things, right? So that's sort of one use case. But I do think, and like I said, maps are always good to have. I mean, I should say, maps are either okay to provide because it's just the nature of a lot of problems, or you probably want to build it along the way, right? Because if you're exploring an unknown environment and to come back to where you were, without odometry sort of getting you lost along the way, the odometry drift, you kind of have to build that map along the way. I mean, that's what I was demonstrating last time, right? It was building up the map, and it was helping keeping the odometry drift in check. But I'm just illustrating here that there's different ways one can put these building blocks together, with map, without map, building the map as you go, and so on. It really depends on your use case. And so I'm just playing around with all these things right now. I'm trying to get it to work on my Romy platform, and making it work a little better, a little less clumsy. So still some ways to go, but making progress.
Very nice demo. Very nice demo of Ross doing path planning.
Yeah, and again, I should point out it's all built. It's building blocks, right? I mean, I didn't have to write a single line of code. I do have to, change a lot of configuration files. There's a lot of things. You're not writing for these particular things that I'm showing you. Again, I'm not writing code per se. I'm just connecting pieces together, tweaking parameters. There's still a lot going on here that's a black box to me that I don't know why it's moving in this clumsy fashion sometimes, and that sort of thing. And we talked about the challenges of ROS, and when you take these very complex building blocks, and you will be lost occasionally because you just don't know what's going on. But so it takes time to deal with that. Of course, I did have to write a lot of code for the basic, data acquisition on the robot, right? The wheel odometry doesn't come about by itself, so that's obviously just standard robot code. But everything RAWs wise, again, it's just building blocks wired up in a certain fashion. Oh, I thought I had a diagram here. Hang on. Oh yeah, so that's kind of the standard diagram that what I was showing here basically is represented here. I know it's a lot of raw specific lingo here, but basically on the top right, where it says map server, you also have this thing going on. It's sending the image that represents the map. It's just making it available. Again, we're not building it up on the fly. And on the bottom left, I have a source for odometry, right? That's my code that I've had for some time now. And upper left corner, AMCL, the adaptive Monte Carlo localization. That's one way, one of the fairly standard localization algorithms that's strictly localizing. It doesn't know anything about building a map. It wants to have a map and match the laser scans against it. So that's what's keeping the odometry error in check. Or I shouldn't say it's not that it's correcting the odometry error. It's just keeping track of, okay, where we are, relative to the laser scan and the map. Um, and the move base, the big box in the middle, is the one that I told where to go through my, pointing and clicking with the mouse. And it's the one that's sending commands to my code, right? Velocity commands that are interpreted by my code, and I make it go at that velocity and that angular velocity. So I had to make sure I'm executing those commands correctly, because a couple of days ago I wasn't, and the thing was just going completely haywire, and that's because my robot was turning left when it was saying turn right, and that's because left means you're going, you gotta have the coordinates, and positive x means you go straight, negative x means you're going backwards, and so on. You have to have all that correctly implemented in your low level code to execute those commands correctly. So, but in the middle of this big box, that's where this you see those cost map things. That's what was producing those colorful images there, where it was taking in like the sensor data and just visualizing it through this accumulating information in these cost maps and then visualizing it. And then ultimately this move base has is the one that has the planners or uses planners, both global planner and local planner, to actually make it move. Again, it's not, there are alternatives out there that I have to still explore. This particular set of building blocks, as I like to call it, has been around for a long time in RAWs, and there's, for many of these things, there are different flavors available. There's different local planners available. Again, the local planner deals with the real-time information. There are different global planners available, and then they all have different parameters, right? So there's lots to try and to tweak, and those. So that's kind of what's in part what's next. Questions?
Gold stars, man. That's Ross on a Romy navigating around obstacles. I mean, that's
sort of navigating around obstacles. Yeah, still very clumsy, and yeah, but we'll get there. We'll get there.
Doesn't get much more high tech than that.
And
high tech for sure for simple problems, but the hypothesis is, once you got it figured out how to make use of all of this, you can tackle much more complex problems. That's the hypothesis.
Of course, we had to trust that it was the Romy and not somebody with a mouse moving it around in the background. But
you're gonna have to trust me on that. I'll show that on some other day.
That's good. Cool demo. All right, so hey, Mr. David, you're back. I hope your internet is behaving better now.
I hope so. So I actually didn't know I had lost the connection, and I went through and gave the whole talk I had prepared, and then came back and found that I wasn't online. So how far did it go?
You were on the second video. It had just gotten past the box. Your audio dropped, and then we could see the mouse moving around at the black tape after it hit the box, and then that video went away too. So the second video.
Well, maybe the Lord just didn't want me to present today. I can jump to another topic. I bought a couple of these. They're just $10. Can you see what that is?
Oh, hold still, VL53L1.
This is the 8x8 time of flight sensors. And I got them on a little breakout board. I don't know if you can see that. They're tiny, you know. They sell them to you on a paper strip. Anyway, I just thought I might play with them. I actually not sure I actually want to go through all that again. I'll just show you the guys the videos. How's that? If I can.
Okay.
All right. Let me try this again. So you guys saw the first and second one?
Most of the second one, or half of the second one at least.
Well, okay, I'll start with this
second one.
And David, I think Dave Ackley was showing the same VL53L1 sensor that you did. So there's now a couple of us in the club with that apparently.
Well, good. So, okay, I don't even remember what the point I was trying to make here. But I demonstrated. See, I can't tell if I'm online right now. Can you guys hear me?
You're online.
So at the end of every sentence, you need to say over.
Okay. We'll give you feedback.
So here the robot can see, the IR can see the box, and it continues turning until the side-looking IR, which is right here, doesn't see the box. And at that point, it drops control, and the navigation control takes back over.
Yeah.
And okay, I think I went through that with y'all, didn't I?
Okay. Well, hey, David.
Yeah.
Just to make sure, though. So after the drops those signals, it still goes forward for a little bit, and then it starts to turn.
Yes. So, okay. So right there, you can see it begins the turn. That's
right.
the IRCs.
Yeah.
And it continues to turn.
Right.
Right there.
Right. And when it clears, yeah, I got it.
Right there is the side looking.
Now watch how far it goes too.
Okay. So at that point, then it has basically a timer. It times out. I believe it's about half a second, maybe less than that.
Longer than that.
Right.
You're still going straight.
No, it's turned.
Yeah, but I mean, okay.
Okay. How about 7/10 of a second? 11/13 of a second.
Yes. It's a relaxed turn.
Yeah.
And so the turn begins there.
There, okay. I agree with that.
And again, there's not, we didn't stop and recalculate a new waypoint. We're calculating continuously 25 times a second. So every 40 milliseconds, it gets a new heading and distance to the waypoint.
Same thing.
Okay, so in there, okay, that's the point I'm trying to make, Doug, is that the behaviors it produces are the same, but it has some real advantages because, well, I'll get to those here, unless I crash. Over?
Over.
Okay.
Sounds like airplane. Captain, over. Roger.
Okay. So then Doug's third test was 3 boxes. So here we're attempting to drive to that waypoint. Right there, the IR sees the box, and you see the left-looking IR is clear, and the right-looking IR sees the box. So we're going to turn left, and it clears the box. And then about half a second later, it tries to turn back to the waypoint, but there's another box in the way. As you can see, the side-looking IR can see that box. And so even after it turns, you see it goes in a straight line there because the box won't let it turn back. Finally, there, maybe slightly before there, the side-looking IR clears the box. So here's the point. Basically, we're measuring the size of the box in real time with the sensors so that it's not turning through an arbitrary angle and driving an arbitrary amount, but rather it's turning exactly the angle required to clear the box and then driving the distance required to clear the box. Basically, as I say, we're measuring the box in real time. And finally there, it straightens out. Okay, so now we enter as a cul-de-sac. And actually, this doesn't do what I expected it to do, but I do have an observation here. Over?
Over. You got it.
All right, we'll do that again.
Oh.
What the robot is doing is it's scanning back and forth. The way that this robot scans, the sensors are fixed and it scans by rotating around its middle.
Yep.
So it's scanning back and forth to find the edges of those boxes. And Doug, I had the same problem with you. I need heavier boxes.
Because your robot said just, screw it, get out of the way, boom. And, went into beast mode.
Okay, but so here's my suggestion. A robot that can get through a little tiny space like that,
yeah,
that's just a good way for a little robot to get in trouble.
Get stuck.
It's just you can get around back behind things you can't get out of.
Yeah.
But it's actually pretty cool to watch it do it.
Huh.
And center up right on that opening.
And it wasn't just center; it was moving in between the turns, right?
Yes, it's actually moving forward in between.
Moving forward.
As it tries. Once again, there weren't like 10 extra temporary waypoints there. There's only one waypoint, but the navigation behavior is subsumed by the avoidance behaviors because they're higher priority. Okay, so am I still there? Over?
Got it.
Okay, now I tried to replicate what Doug was doing, and basically it's a waypoint down the hallway and around the corner. And I've set out a series of waypoints in order to get there. So the first video is like Doug showed, where the robot is just going to drive from one waypoint to the next, just like it did in the previous demo. And you can see where the waypoints are. So it rotates toward the first waypoint, and the navigation drives toward the first waypoint.
Yeah.
And I didn't put the first waypoint in a good spot. So we're going to hit the door here.
Dope.
But the IR sees the door and pushes the robot away, and the navigation takes back over and recalculates the heading to the waypoint. So here's the second waypoint.
Yeah.
And you notice that I'll point that out later. The third waypoint is right here in the doorway.
Yeah.
We slow down and come to a stop. And the fourth waypoint is down at the end of this hall. And let me replay that. You can see that if you look carefully, that the robot very slightly turns right just as it leaves here, right there. That's because the IR saw this door and it pushed us away from the door, but only for a fraction of a second.
Yeah.
Okay, so I wasn't real careful about laying out these waypoints, and there's actually a black metal trash can in the way here. I don't have the sonar turned on, or they would see it, but the IR, it doesn't get a reflection, so the IR can't see it. This is sort of like some of the problems that Chris was just talking about with, a dark surface.
Yeah.
And you can see at the very last instant, it starts to turn, but that's not enough. So at that point, we have a bumper behavior. It actually presses the bumper. And the simplest bumper behavior is back up, rotate, drive forward, release. So that's what it's going to do here. Bump, back up, rotate, drive forward, release.
Yeah.
And at that point, the lower level navigation behavior takes back over. Here is the fifth waypoint in front of this door.
Yeah.
And then if you can see, there's a piece of tape lying down there, which is the last waypoint.
Yeah.
Okay, and this is kind of interesting, Doug. This takes us back to our odometry versus navigation. If you look here, well, let me wait till it comes to a stop.
Yeah.
Okay, what's happened here, this is interesting. Okay, this is the Y direction, and this is the X axis. And you can see on the Y direction, this is about a 12-inch robot. So the center of the robot should be about there.
Yeah.
And so we're off about 6 inches in Y. But in X, we're bang on. It's hard to see how I could do any better than that. And so bang on in one axis, 6 inches off in the other, and I'll come back to that. Okay, so this next video is the same thing, but because the robot is calculating new distance and angle every 25th of a second, we don't have to stop at the waypoints in order to rotate toward a new waypoint. We can actually do that on the fly. And that's what it's going to do here. It's only going to stop at the last waypoint. So we don't rotate toward, we actually arc toward the waypoint. So there we arc toward the first one, and it's not going to slow down and stop there's a little red LED in the middle. If you can see it right there, it tells us when we're getting to the waypoint. And now it takes the next point and calculates the distance to it. If you look, so there's our second waypoint in front of the door. We grab the third waypoint. And as I say, it's correcting that steering 25 times a second. So we don't actually have to stop, rotate, and pick a new angle and then drive it a straight line. We can actually drive in arcs, which is not only more efficient, but it's more aesthetically pleasing. And you'll also note that I moved that trash can, although we wouldn't have run into it. Here's the fifth waypoint, and then finally the final one there.
Yeah.
When you're calculating the turn, I mean, you're not turning as fast or as hard as you can. What are you doing? Are you doing some sort of bid or what?
The turn. This is a whole other discussion, Dave. The turn is controlled. There's a turn constant, and if that's all that was in control, then it would just turn at a constant speed, and you just pick a handy one. But also, if you remember from my talk, the speed of the robot is independent from the rotation, and as the robot slows down, the turn gets tighter. So you actually control the amount of turn by how fast the robot's going for a fixed angle. Does that make sense? So, for example, if we go back to
what you're saying is that if it says I need to turn, then you just have a certain fixed amount that it will do a turn.
There's a constant there, but that constant is adjusted by the speed of the robot. So if you look at this turn right here, it slows way down, and therefore it almost does a 90-degree turn. See that?
Yeah.
Versus what it did
early
back here, which is just a very
swoopy.
Yeah. Okay. So, okay. And as I said, the point I'm trying to make here is that by, like a modern sailing vessel, by constantly calculating the heading to the waypoint and keeping the waypoint ahead of you, then the robot will automatically respond to perturbations if it gets shoved by one of its other sensors. Okay, so here's the last run, and I agree with Doug on this. The most fun is when you just have one waypoint, just the final waypoint, and the robot's got to figure out all the rest of it by itself. That's when it gets to be the most clever and the most creative and also get in the most trouble. So in this is the same as the last run, except the robot only has the final waypoint. It doesn't have any other waypoints. And the final waypoint, as you may remember, is over here somewhere off to the left. So I say go. Whoa. So it heads straight toward that waypoint, but there is a building in between us and the waypoint. Velocity slows down, and so it rotates in place looking for a clear, and there it is clear. So the navigation takes back over and tries to go back toward the waypoint, but it can't because there are things in the way. In this case, I'm running the sonar and the IR, so the sonar is running, and it can see further away than the IR can. So finally, we're clear of all the obstacles, and it can turn back toward the waypoint. If you look as it goes through the door here, you see right there it swiveled left because the waypoint is like over there. But the IR saw the door and straightened it back out. So, in point of fact, the robot knows nothing about this architecture, but it not only found the door, but it found the exact center of the door. And that's all because it's reactive. It's navigating reactively rather than by planning, which I know I'm the only one on the universe that does it that way. The same thing here, and you can see it, those obstacles pushing it away, and it again not only finds the door, but it does a pretty good job of finding the center of the door. So basically you can think that anytime the robot here is turning to the left, it's trying to get to the waypoint. Anytime it's turning to the right, it's being pushed away from an obstacle because we're going counterclockwise here.
So I wonder if it was a different construction if there could have been like what was in the other context, a singularity trap.
Well, this guy won't get caught in singularity traps. He's smart about that.
Because it's got the wall following escape behavior.
Well, and it's not wall following here, but there are other ways that you can avoid that.
Escape. Huh.
So this is interesting here. So, okay, with only one waypoint, and it found its way pretty well.
Yeah.
That last waypoint. Okay, now check this out. If we look at our y-axis, it's about right.
Yeah.
We might be off a half an inch or an inch maybe, but it's about right. But the x-axis, we missed by about 7 inches. Okay, and I've seen this before, actually often. And basically, usually what it means is that when I initially set up the robot back over there in the lab, I didn't have it lined up exactly square with the building. And if you're off just a fraction of a degree, y will be correct, but x will be off by that fraction of a degree. So this is why I was saying the way Chris is doing it is really cool, because it sort of automatically falls out of his approach that the robot can get square to the building, or square to the walls. So, and in this case, if we go back to the beginning of the video, basically what I tried to do was line up the robot with this piece of tape and then get the front of the wheels to touch the edge of this stripe here. And that's not very precise. On one of my robots, I've got a laser pointer mounted on it, so you can use that to get repeatability, which is pretty cool. So I believe these behaviors that I'm showing here are not doable by dead reckoning, and that's one of the reasons that I'm attracted to doing it this way, and why I think is a more powerful way to navigate than by successive temporary waypoints. And that's all I have to say about that.
Gold stars. Very nice. Look at that. I don't know about anybody else, but this is starting to make sense, David. From the presentation, the excellent one you did earlier this year, to our regular discussions now, and seeing similar videos in different contexts, this is really helping me understand, at least. I hope it's helping others as well.
Well, I'll keep saying
it. Very good.
So if I may offer a commentary on both Chris's and David's demonstrations based on the self-driving trucks that I worked on. The demonstrations that both of you showed are really centered on the idea of there being sparse waypoints that are fairly widely spaced. They don't have to be, but that's what was shown. And the robot is largely in a desert where it can drive wherever it wants, other than the obstacles that it may encounter on the way. And so, just as the contrast that I want to bring out is that with vehicles, you really are never in a desert. You have roads that are really important to stay on, and so the way the robots I worked on were designed was to follow a very closely spaced set of waypoints, about 1 meter apart each waypoint, and to use an algorithm called pure pursuit, where the robot attempts to reach a point which runs along this track of waypoints, and so it's always heading towards this moving point that it never reaches, because the point is like a carrot in front of the donkey. But that's an appropriate approach for driving on roads. So I thought it was just interesting to see the environment that you two guys presented for navigating in a desert of an office with obstacles versus driving in a very route constrained place like a road.
Paul, I remember with the DARPA challenge, the grand challenge, that I was real shocked when I downloaded all their materials and saw the waypoints, that they were just a few feet apart. And I remember at the time thinking I'd be more interested if all they told me was where to go, where they want me to arrive at, and let me pick the route. might drive up and get on the superhighway, you know. But I also found, and is Doug still here? Doug has seen the same thing. With driving along a list of closely spaced waypoints is not a trivial thing to do. And if you miss waypoints, you know, what do? Do you ignore them, or you try to go back and get them? That can get real complicated. It's not trivial to drive.
Well, the pure pursuit allows you to miss waypoints and still head towards where the dot is that it's trying to follow.
So why do you need those waypoints?
To keep it better centered in a roadway, constrained to a narrower space, because
the waypoints act like an attractor to identify a path that you need to follow. That's the same approach that I took with the outdoor rover, where I'm trying to trace out specific paths on the ground, right? So the goal isn't just getting to a certain location; it's getting to a location along a certain path.
That's when you were
that might not be constrained by other kinds of
sand and so forth.
Pardon?
You're actually writing words.
Right.
So I guess that's an interesting point that you raised, Kareem, that they're really, these two approaches are solving different problems. One is solving get to a point in a desert with obstacles somewhere in it, and the other is solving a problem of stay fairly close to a predefined path while getting to the end wherever that path leads. Anyway, that's all I want to observe.
So, Paul, and the machines you're working on, is it the lead truck that's dropping the waypoints? Is that how it works?
And is that something you're going to describe more when you do your talk, Paul?
Yeah.
Cool.
Really? So the other trucks just follow the lead truck?
Yeah.
Wow.
Yes, convoying. Okay. There were multiple modes. It also had a plane drive a path and then replay it and follow it. Kinds of modes. And
I also have to point out that Paul had the luxury of running these big, heavy, dangerous equipment in a totally fake town, like a Hollywood set, so that it couldn't hurt anybody.
Just rain on his parade, David. Just rain on his parade there.
No, I mean, it looked pretty cool. They actually have built an entire town to drive these autonomous cars around so they don't hurt anybody when they screw up.
Well, actually, those were on Army bases, and they're called MOUs, Military Operations in Urban Environments. And one of them quite closely resembled something you might find in the Middle East, with various bits of buildings blown off from where apparently they'd been shooting at the buildings. So they're really more general purpose environments. But since I'll tell just one more story and then get off. I was safety operator on one of these trucks, meaning sitting at the wheel, letting it, driving it, and then doing routes. And I was sitting crossways across a road, and suddenly I hear across because I had a nav guy sitting beside me, I hear on the radio, "Clear, clear!" And I look up and there's this convoy coming towards me down the road. So I stood on the gas and took off crossways and into the town so they could get by on the road. I was like, whoa, that job was more fun than I should be allowed to do.
And Paul was never heard of again.
Yeah. Anyway, great demos, though.
Yeah, very
by both
cool.
David and Chris.
Those are French underwear, right?
All right. Well, I think since those were such excellent demos, it lasts several. It's time for lowering the bar a little bit, I think. So I'm going to lower the bar considerably. So last week we had this discussion about behaviors which shall be named because they lead to hours of discussion, and but it got me to thinking because I suddenly realized last week that in however many years I've been doing this since DPRG got me started, I've used cameras as sensors, I've used IMU as sensors, and I've used encoders to measure wheel velocity, but not position. And those are the only sensors I've ever used. So last week when we had this discussion about bumpers, and I asked if, and I was provocatively challenging whether a bumper could be used as a behavior which shall be not named, because we're not worried about names. And it got me to thinking, because I'd never honestly, I had figured that bumpers, they're too far below me. I'm not going to worry about them. I'm going to mess with computer vision and cameras. So then I got to think, well, what would happen if I had a bumper? And then I thought, I got 4 robots and not a single one has a single bumper. And then I thought, well, how can I mock this up? And I thought, well, it's a good thing that I got started with my with this little robot for my 10-year-old cousins, because I figured I could do a mock-up thing and use IR sensors instead of a bumper. So what I did was I sat down in this really I'll even show you on the screen here first. I'll show you where did it go. So I dusted out this highly complicated advanced programming language, and I wrote this program in Scratch. So there it is. Okay, it's a secret, so I can't show it for too long. Oh, wait a minute, that was for Murray. I wrote this really complicated program, and I pushed it to the robot, which only has IR sensors, no actual switch bumpers. And what the program does, well, I can't change the camera. What the program does is that it basically has the IR sensors wired up to the wheels. So I have 2 IR sensors, a left and a right. They are like here, right? Maybe, if I point to the camera, right? So a left and a right IR sensor. So what I did was I have the logic that says, if it's seeing black, then we're going to go forward. If both are seeing white, then it's going to go backward. And if one side is on, then the other wheel it'll turn one direction. If the other side is on, it'll turn the other direction. So that program, it doesn't have any timing except for what it takes to execute from one line to the next, and what it takes to read the line sensors. But basically, so you can imagine it's the basis of a sumo robot then, basically. But it works in any direction. I'll turn it around here and let it go. And it just, fine. It just tries to avoid the white line. But the wheels are always following however fast it iterates through the loop, they're always following the instructions of the, in a way, of the IR sensors. So is it the one behavior that shall not be named or the other behavior that shall not be named? I don't know, but as long as the wheels aren't turning too quickly, it does a nice job of staying within the thing. In fact, I did this last night on a tiled surface, not the carpet in my office here. And it had that jittery back and forth thing so much that it kept slamming down on the tile, and some screws fell off. So not much of a demo, but
duct tape and baling wire, man. Duct tape and baling wire. I thought you were putting a copyright on that methodology.
I am, but this was somebody else's. This was beyond duct tape. This is actually made pretty nicely. I just didn't use Loctite until today.
That's awesome.
But anyhow, as simple as that is, That's at least I feel good that I actually made a robot move this week.
Gold star. Gold star. Right there on the forehead.
So,
Okay,
a
Carl.
wrinkly, crumbly, dusty old gold star, but okay.
I have the lead in for that. You're like my lead in man here.
Oh.
Okay. Yeah.
Okay, so you're next. So that's all I had. Unless anyone has some questions, like if you'd like to see that highly complex code that I wrote, it's a very advanced program. It uses variables and blocks actually, so it's modularized. I can export the sprites if you want to copy it. I don't know how to get it to GitHub just yet, but
yeah. Why I say that is because after having achieved my initial goal of going from one place to the other place on a single waypoint, I looked at what's screwing me up the most. And it was I didn't have a bumper. I'd bump into, my sensors would not see, just like David's black garbage can. I just wouldn't see it. And I have no bumpers, just because like Carl, front end space on my robot is too valuable to put a stupid bumper on it. Well, I decided that I better get a bumper. So I spent some time this week looking at bumpers. And I'm going to show. So, no, I didn't want to show that. Give me a second here.
Yeah, I can remember we used to call the bumpers the sensor of last resort.
Yeah, yeah. Let's see. How do I change layout from? Oh, this must. Yeah. Okay. All right, I'm going to do some presentation here. The first thing I wanted to show was some ideas that I gleaned from the internet. And let's see, this right here was what caught my eye. And I said, oh, this is a nice, simple, easy to make bumper. Seems to be pretty good. And what I did is I saw it in a YouTube video, but the guy didn't list his source. So then I went to Google Images and finally found it. And it's some company in England that makes this, but you could obviously make one yourself. But then I also, while I was out there, saw this. And this is really cool because if you look at it, he's got a rubber band. And that means that if he hits it here, or whether he hits it here, or whether he hits it here, it all perturbs the switch. Now, because now I'm going to switch out of this and show you, if you guys would go ahead and pin me, I wanted to show it this. So here's the basic idea of that, but it's a little different, and I just wanted to show how it moves. You see, it's very responsive to almost any direction. Now, what I decided to do was, now I'm going to present again. Decided to do this. This is my layout of that. And so, like Carl, I decided I'd use an IR sensor, but I'm using it a little differently. What I'm doing is I'm putting IR diode and IR photo transistor across here. And there's a little hole through these two stubs. So, and this is where the rubber bands go. You can see, I haven't put it on it, but you can see the idea. And this is the base of the robot. I haven't printed it out. That's why it's not assembled. So this is my first shot. I'm going to try and make this. What I want to do is try to make a robot module that's easy enough to be put wherever I need one. So anyway, so that's the robot. I wanted to show you on bumper, but there's a couple of good ideas, I think. Then the next thing I wanted to show you, if I get back to This is, okay, let's see, I'm sorry.
One question, Doug. The
Yeah.
the design you just showed for a bumper doesn't have almost any height to it.
Yeah. Well, my first thought is in most of the controlled environments that we work in. Now on my rover, there's a different design, but I'm talking about indoor arena type robots. We don't necessarily need height, but you could make a cow catcher out of it. It's all 3D printed, so it's not that you can make it as wide as you want to. But I don't want it above my deck, my sensor deck. I want my sensor deck to be able to see all its sensors an unobstructed view. So this is actually going to hang underneath the sensor deck, which is that little ramp. So that
okay. I was just checking checking on the design, so it could get trapped under a chair, for example.
It could. Well, it probably could get trapped on one that had a where it comes down two legs and then it has a bar across the floor. That would be a bad spot. But two legs, no problem.
Thanks,
Doug. I was going to make the same point. Chris was talking about his LiDAR not seeing things above or below the scan line. And I've seen that same problem with bumpers and I can give you half a dozen examples. For example, the tail end of a rocking chair, sticking up that you can run into. The what's the little toe thing? When you have kitchen cabinets, you got a place for your toes to go. Where the top part of the robot can run into that, the bottom part. So it's problematical just to have a narrow bumper like that, I have found.
Okay, I'm crawling before I'm walking, I guess. If this works, and there's no guarantee it should work, but mechanical design is always kind of a little quirky until you actually mount it on your robot. But there's no reason.
Walls and furniture and things like that will probably work, but there are odd cases.
Oh yeah, and like I say, I don't really want to go up. I don't mind going down. It's easy to go down, but going up, if you go down, you run into that situation where if you can go over it, do you really want to be stopped by it? And also remember, this is the sensor of last resort. Okay. So this means that it's defeated all of your IR sensors. Your sonars didn't see it. Your LiDAR didn't see it. But more often, the reason why I want to do it, David, was when I was driving through the boxes like you did, I would catch an edge of a box. When you were wiggling through the two boxes, this would be a corrective way to handle that. That's what I was looking for. Now,
I would suggest your sensor of last resort should be a cliff sensor. If you got downward sloping stairs anywhere in your environment.
Oh, I agree with that too. But I don't think this robot will never have that problem. I live in a single floor house. Anyway, but the other thing I wanted to share with anybody, I mentioned this last week, this CZ zone, I've now worked my way to about 2/3 of this course, because I only hit it about 15 minutes a day or so. And I definitely recommend it. It's free and very, very worthwhile. This one happens to be in Python, but he also has one in C++, but I'm doing the Python first. And if you don't know anything about OpenCV, this is a real eye opener, and I really recommend it. And well, so now I got down, before when you go to face recognition, usually the first thing they talk to you about is a HAR cascade. And so I started thinking, he presented it in such a way saying, well, it's not just faces. And so I took him up on that and started looking. And guess what I found? Whoa! So anyway, why this guy is really useful is because he goes through it step by step, talks about how you collect your images, everything, and it's all OpenCV. There's nothing out of OpenCV that is used for this. So anyway, I thought I'll put this link in the chat, and I just thought I'd share that with you guys. Okay. And if I can get stop sharing, and
thanks, Doug. I'm filing that away for when I get to that point.
yeah, well, it's like I say, if you take the course, the little 3-hour course, you probably would be ready to at least give it a shot. And it's like I say, I recommend the course, and
Cool.
yeah,
Very good.
yeah. Unfortunately, it doesn't give you the Cascade XML, but well, can't have everything. So,
Murray, we heard you got rid of your wizard and have an outbreak of COVID.
Yeah, not good news.
those two
It's
things
to the point where we've got a whole bunch of anti-vaxxers protesting, and we've got this guy named Brian Tamaki, who's Maori, who runs a church theoretically, but it's really a tax avoidance.
Here we go.
And they're all protesting getting vaccinated, and they're hanging out in big crowds and basically infecting each other. So yeah, we're on the downward spiral now. Oh, the wizards! Yeah, we get a lot of wizards here. There's a whole bunch of the whole Lord of the Rings thing took off here, and we've got, I think there's about 20 or 30 alternate religions.
I'm not saying. I'm just saying you got rid of your wizard and suddenly you had a COVID outbreak. I'm just saying.
Yeah, I didn't see the connection. Yeah.
Wave of the wand, you could have gotten rid of COVID.
I think the natural selection will take care of the vaxxers.
Yeah, sadly. But unfortunately, if you look at the statistics on this, the people who are going to be most affected are poor Maori people. They're the least vaccinated in the country. So and they live in larger communities and have more contact with each other and are more religious. So they go to church together, and just all those scenarios suggest that they're going to get hit the hardest.
They play rugby.
And they also don't trust the government. So
they all play rugby together. That's the super spreader event.
Yeah. It's a bizarre place to live in some ways, but not any more bizarre than where you guys are. Come on now.
Plus, it gave us Paul, so there's that.
That's right.
You win some, you lose some.
How long you been out of New Zealand, Paul?
35 years.
Oh my. That's like me calling myself a Canadian. I haven't lived in Canada since I was 11, so.
Yeah. I was wondering where your accent was from. Okay, got it.
I would have to say my accent is probably Californian. That's where I lived most of my adult life.
Okay.
The A comes in every once in a while.
Yeah.
It still happens to me every once in a while. I left when I was 12 from Canada.
Oh, are you Canadian citizen?
Yeah, Canuck.
Oh. There's lots of Canadians here, huh?
Leafs are Canadian.
He lives in the blistering heat of Texas.
Yeah. Well, give it another 10 years of that blistering heat here.
It was still the strangest thing that I ever felt at the age of 12 was a warm wind. I'd never felt that before, but the minute I stepped off the airplane in Dallas, it was just bizarre. I had no way to process that. Yeah.
I mean, that's what happened to me when I came down from Pittsburgh, Pennsylvania, and it's not quite as cold there as it is above the border. So
I think Paul can recognize this one. The strangest thing for me in moving to New Zealand was that the phases of the moon go backwards.
The moon is upside down. They're not backwards. It's the fact that it's upside down.
Yeah, I know that. But the point is that when you watch the moon, it doesn't go the same way. It's like, whoa, that's weird.
It's all that water swirling the wrong way is what's doing it to you, man.
I don't spend a lot of time looking into toilets, by the way.
We worry a lot about falling off, though.
You find that you have north and south reversed a lot, Murray? Because I do, even after 35 years. I look up the beach that's north and I say that's south, and it's because the sun's in the wrong hemisphere.
Well, I would say that would probably be the case, but for some weird reason, I always seem to know where north is. It's just kind of like when I did a lot of hiking when I was a kid, I think, and I just always seem to I don't know, I've got a compass in my head or something, but the weird thing, of course, is that the south side of my house is the cold side.
Yeah. I would always come out of the tube when I lived in London and head in the wrong direction. And one day I got lost driving back into London and was late for a meeting with my boss. And I walked in and told him, sorry, I got lost because the sun's in the wrong direction and I went in the wrong way. He thought it was the best excuse he'd ever had.
Paul, I have a colleague that went to New Zealand to do some work. Evidently, there's a lot of geophysics interest in that part of the world. And it's been a couple of years over there, and I asked him what he thought about it. He said, oh, I loved it. It's like it used to be here. And I said, is that really true? And he said, no, it was never like that here.
Yes.
Well, there's a certain 1950s sensibility that still exists here. It's still kind of like the 1950s here.
Sensibility.
And we have high tech and everything, but I just got off the phone with my insurance company. I've been trying to get my basement leak fixed for over 6 months now. And since March 31st. And I'm on my 6th plumber. And it's just ridiculous. And part of that is this kind of old school, we'll kind of get it fixed when we get it fixed, kind of like, well, it'll all be right kind of thing. And it's just like, oh, come on, whatever happened to professionalism? There's no insulation in my walls. It's all single pane glass. This house wasn't built in 1945. It was built in 1966. And there are houses like two up from me, which was built in the 90s, which still no insulation and single pane glass. It's just like, come on.
Luxuries.
Yeah. It's a 1950s kind of mentality. You just put on more clothes and you don't care that your house is hot or heated, I should say.
Grab the propane heater to warm the room up. I mean,
and then there's guys wandering around in front of my house, in the wintertime in shorts. So it's year-round shorts and boots, like rubber Wellington boots, what do they call them in the U.S. now? Rubbers? No, we call them rubbers in Canada.
Galoshes.
Galoshes, yes. Yeah, thank you. And so there's lots of guys wandering around in galoshes with shorts year-round.
Well, that's also a cultural thing. Somebody showed me a cartoon, and it was 2 frames. And one frame was 40 degrees in Minnesota, and the other frame was 40 degrees in Miami. And in Miami, they all have on like coats and sweaters and and in Minnesota, they're in their shorts and they're throwing frisbees in the park and having picnics.
Yeah.
That's the way we are here. It's a freezing 32 degrees F, and we're outside barbecuing. It's still season.
When I first moved to Wellington, I moved to one of the suburbs. The southern suburb of Wellington is Island Bay, and it looks out over the strait to the south island. And it gets pretty cold and windy there. Wellington's probably, I think it's the windiest city in the world. And so you get big winds, big waves. And I remember right after a big storm, I was walking on the beach, and this is midwinter, and there was 2 very attractive young girls in bikinis in the water. And I walked by them, and as they came up, I said hi, and I said, "Aren't you guys cold?" And they go, we're working off a hangover. good idea. But yeah, I don't think I'd be going swimming with the girls around here, though. Might be tempted.
Too much shrinkage, I think.
Oh, what was the name
ow,
of this?
ow,
What was the
that's
name of
usually
those
my
those
job here.
tight shorts from the 70s?
What's the name of what?
Snuggies. There was a pair of there's this whole thing. They even did mock advertisements for it. It was a form of short trousers that were tight fitting from the 70s.
Stubbies.
Stubbies, yes. If you go on YouTube and search for New Zealand stubbies, there's this great ad that they did that was a fake 1970s ad of a guy in stubbies drinking a little bottle of beer, a brown bottle of beer. This is a great ad.
I must confess.
Yes.
Stubbies. Yeah, it's sort of like what are they in European beaches? They get guys wearing those little tiny G-strings budgie smugglers.
This is Speedo.
And, Speedos, yeah. And stubbies aren't quite like that because they're covering, but they're way too tight.
Okay, too much information. We're
Too much
scaring Dave Ackley away.
Yeah, TMI. I'm
Way
out
off
of here.
topic.
All right. Yeah, anyone else have any on-topic points for the night? I'm seeing waves.
I was on the insurance call. I missed out my chance. I'm sure I'll have to pick it up next time.
We'll catch you up next time.
All right. It's good to
Well,
see you
hurrying
guys.
on, it just sounds like we've gone past the.
Hey, I got a question before you wrap up.
All right.
Who is Shurik 179?
He's a math professor from upstate New York who's originally from Russia.
Okay, but is he here?
No,
Does he go to these
no.
meetings? He never goes to these meetings.
Nothing to do with the DPRG at all.
Yeah, because I was gonna connect with him this Friday. I don't know if you saw that.